Welcome. Today we shall see the input-output structure of flowsheet. That is the second lecture of this module, flowsheet synthesis. In the previous lecture, we saw as what input information is available when we start designing a process. We have reaction, basic chemistry of the reaction, the stoichiometry, the reaction conditions, the catalyst, so on and so forth. And then we saw as how this information needs to be improved when we start designing a large scale process from a laboratory experiment. For example, we need to know the purity of raw materials. The raw material that is used in the laboratory experiment is very pure, but that purity may not be achievable on commercial scale. Therefore, we have to see as what side reactions or what impact the impurities in raw material will have on the process. Okay. And then we saw as what factors govern the selection of batch versus continuous nature of the process, whether we should go for a small scale batch process or a large scale continuous process. Now, we found that there are several factors that affect this particular decision. First is the market force, the type of product that you have, the lifetime of the product, okay. So, and then other factors such as process constraints, like suppose your reaction contains a material that is thermally decomposing, which can form coke and deposit on the reactor wall, or you have reaction conditions in which fouling will occur, where you will have to shut down the device, the reaction vessel, and clean it very often. So, in those conditions, continuous process is not possible. And then we saw the level of or the kind of decisions that we have to make while designing a continuous and batch process. Now, in today's lecture, we go one step ahead and then see the input-output structure of the flow sheet. Input-output structure of the flow sheet essentially means drawing a box around a process and see what are the raw materials that are going into the process and what are the products that are coming out. Okay. This is essentially the level 2 of the hierarchy of decisions during process flow sheet synthesis. The first decision we have already seen, batch versus continuous. Second will be the input-output structure of the flow sheet. Third will be the recycle structure of flow sheet. Then comes the separation systems, and then come heat exchanger network. Okay. So, we are at the level 2. Let us see what decisions we need to make for the input-output structure of flow sheet. In the most general form, the input-output structure will look like this: a box representing the process, and then the reactants going in or the feed streams, and then products as well as byproducts coming out of the process. Another structure of flow sheet could be that including a recycle and purge stream. Now, under what circumstances we need to use a recycle and purge, that we will see in the later part of this lecture. Okay. So, this particular flow sheet would look like this: the feed streams going into the process, products and byproducts coming out. And then there will be a recycle stream and purge stream. Why do we need to assess the process with such kind of flow sheet? In many petrochemical processes and also other process industries, the processing cost is about 30 to 80 or even 100% of the raw material cost. In such cases, we need to assess the value addition of the process. We need to do material balance from outside process, as what is the total cost of material that is going in and what is the total cost of material that is coming out. And then if that economic potential is promising, then we need to go to the next stage. Another thumb rule is that we have to recover 99% of all valuable material. Now, as you will see in both of the general types of flow sheet, no reactant leaves the process. That means, we recover all valuable reactants to almost 100% and recycle them into the process, because in many processes the value addition is limited. So, the loss of reactant could adversely affect the economy of the process. Now, some reactants could be lost. And what are those reactants? The one that are cheapest, for example, air or water. Now, we would not like to recover air, because air is free, you can use as much as you can. Okay. Water in some cases is recycled into the process if the process plant is not located in a locality where water is abundantly available. Now, those factors we are going to see in detail in process economics part, so we do not discuss them here. Okay. Now, as far as the purge and recycle streams are concerned, these are used when you have gaseous reactants. With impurities, or you have a gaseous byproduct. Which could be maybe a side reaction. If we recycle all the gas that comes out of the process, which includes the unreacted reactant, then these impurities or byproducts may get accumulated into the process, and which would make the recycle loop larger and larger, and then ultimately that will hamper the process. Okay. In some cases, the byproducts can trigger further side reactions. So, it is very essential to remove these byproducts from the reaction. In many cases, the gaseous reactants are fed in excess to force complete conversion of the limiting reactant. Example of this would be excess hydrogen fed to HDA process, hydrodealkylation process, to force higher conversion of toluene. Now, we saw in previous lecture that methane comes as an impurity with hydrogen. Methane is also generated in the reaction. Therefore, it is essential to keep the level of methane below certain limit in the process, and hence a purge stream is used. But obviously, hydrogen is also lost from the purge stream. So, that is a loss of hydrogen occurs in the purge stream. Now, recycle and purge streams add a degree of freedom to the process design. And the variables that represent this degree of freedom are the recycle to purge ratio, how much gas you should throw out as purge, and second, the composition of the purge stream. Another variable that comes indirectly with recycle and purge stream is the molar ratio or excess of gaseous reactant that is fed to the process. With this introduction, now we shall see what are the decisions that we need to make while deciding the input output structure of the flow sheets. Now, as we saw, input output structure of the flow sheet is the level 2 of flow sheet synthesis. Now, the decisions are, in the first place, do we need to purify the recycle stream? Oh, I am sorry, that do we need to purify the feed streams before they enter the process? Then, should we remove a reversible byproduct from the process or from the reactor effluent, the stream coming out of the reactor? Then the third decision is that is a recycle purge stream needed? Then fourth is that how many product streams are required? And then should we recover and recycle unreacted reactant? And finally, listing of the design variables. And then the economic trade-off associated with these variables. As we will see in the following discussion, every variable will have two sides. It is like two sides of a coin. If you increase that variable, some benefits will occur, some demerits, and if you decrease that variable, some benefits and some demerits. Okay. So, that is what we mean by economic trade-off. Okay. Now, let us see each of these decisions one by one. The first decision was the purification of the feed streams. Now, purification will necessitate designing of a pre-purification system. Now, in some cases, you may like to feed the process from tail rather than head, which means if the impurities present in the feed streams are also byproducts of the reaction, then it is a good idea to feed the process from back, so that to feed the process from front, so that these impurities get removed along with the byproducts of the process, and then relatively pure streams can be obtained at reactor inlet. However, we may not know what kind of separation system that is required to purify the feed streams. But still, let us see under what circumstances we should purify or we should not purify the feed stream. So, some guidelines for decisions are as follows. Of course, these guidelines are qualitative, not quantitative. First, if the feed impurity is not inert and is present in significant quantities, it is better to remove it at the inlet of the process. That point we note, feed impurity not an inert component, which means it is going to trigger side reactions, give further byproducts which would complicate the separation system design. Then the next guideline is that if the feed impurity is present in the gas feed stream, first consider feeding the process with impurity. Now, why is that? Because separating impurities or gaseous impurities is difficult. We require a membrane process, which is an expensive component in terms of both capital and operating cost for the process. So, when you have an impurity in the gas stream, first consider feeding the process with impurity. Okay? So, that point we also note feed impurity present in gas feed then consider feeding the process with impurity. Now, of course, if the impurity is a catalyst poison, then we have to remove it at any cost. So, that point we will deal later. Okay. Then, if the feed impurity is present in liquid stream and is also a byproduct of the process, as I just said, then it is better to feed the process from head rather than tail. Then, if the impurity is in large quantity, whether it is inert or not inert, that does not matter. If impurity is in large quantity, then it is better to remove it, because it will unnecessarily oversize the reaction equipment. However, the word large is qualitative. There is no quantitative guideline as how large is large. Okay. So, that point we note, if impurity is in large quantity, remove it. Okay. Then, if the impurity is in liquid stream, but forms an azeotrope with the reactant, then feed the process with impurity. Azeotropic distillation is one of the expensive operations of chemical industry. So, if you have to remove an impurity that is forming azeotrope, you have to go for either extractive distillation or add an entrainer, which will add to the cost of processing. So, it is a good idea to feed the process with impurity. Now, depending on the process, it could be that the impurity is easy to separate from products than reactant, and then you can afford a feed with impurity. That point we also note, that if the impurity is easy to be separated from products than reactant, then feed the process with impurity. And finally, if the impurity is a catalyst poison, then we have to remove it no matter what cost is involved, because catalyst is one of the most expensive components of the process. Okay. So, that point we know, if the feed impurity is catalyst poison, as many sulfur containing gases or sulfur containing liquid reactants, we have to remove the impurity. Now, if we are not sure that any of the guideline that we choose for designing a process is correct, then we list the other option as process alternative. So, process alternatives could be generated with these guidelines. Now, what are the economic trade-off? with feed purification. One side of the coin is that you have to design a separation system to remove the impurity. So, you have capital cost, additional capital cost, and then the operating cost for the system. However, the benefits from feed purification is that better selectivity, better yield, and since selectivity is large, you cut down the cost of separation system. Okay. So, the reduction of load and hence the cost of separation system. Now, both of these factors are reaction specific or process specific. You cannot use any of these as a general guideline. So, the decision whether you have to purify the feed stream or not depends on the process. For example, in the process of caustic soda manufacture using membranes, the brine has to be purified to ppb level to reduce the content of hardness like ions like calcium, magnesium. Now, this would require use of expensive ion exchange resin columns. However, if you do not purify brine to that level, the ions that are present like calcium, magnesium, they can damage the membrane, which is far more expensive component of the process. Therefore, you have to go for a feed purification system, although it adds to additional cost of the process. Now, let us see recovery and recycle of byproducts. Especially the reversible byproducts. Now, this we shall see with the example of HDA process. I would write again the basic reactions involved in HDA process. Toluene plus hydrogen gives benzene plus methane, and 2 moles of benzene combine reversibly to give the byproduct diphenyl with liberation of hydrogen. If we recycle diphenyl rather than removing it, okay, then it will build to an equilibrium level in the process and will stay constant. Okay. If diphenyl is recovered and recycled, it will build to an equilibrium level in the process. Now, to accommodate this additional component, you will have to oversize all pipelines and also the reactor and separation system. However, we save the cost of equipment used for separation of the byproduct. And we also save the loss of reactant in the form of byproduct. Now, let us see these trade-offs with example of HDA process. If you recover diphenyl, then toluene loss in the form of diphenyl is eliminated. Second, the distillation column separating toluene, the unreacted part of the toluene, from diphenyl is eliminated. However, diphenyl is used as a fuel in the process. So, you will have to buy now an alternate fuel. And then, as I just said, you will have to oversize the equipment and pipeline. Now, let us see what factors govern decision on gas recycle and purge stream. As I mentioned earlier, gas recycle and purge stream adds a degree of freedom to the process in terms of the ratio of recycle to purge and the composition of the purge stream. However, when gas stream should be purged, okay, in the first place we will see what reactants can be characterized as gas. Now, in process industry, these components are also called as light ends. So, we have to first see the criteria for a light end. Since the transport of liquid stream is much easier than the gas streams, for liquid transport you only need a pump. Okay. You would like to have as much of your reactants in gas phase as in liquid phase as possible and avoid gas stream. But in some cases light ends cannot be avoided. So, for light ends, okay, we use the criteria of liquefaction. Okay. To liquefy a gas or vapor stream, you need to compress and cool or condense. Now, cooling could be with simple cooling water or with refrigeration. Now, if we define a light component as the one which condenses using cooling water when compressed at moderate pressures then we can use propylene as a basis. Propylene will condense with cooling water when compressed to pressures about 8 to 10 bar. Okay. Therefore, if the boiling point of a particular component is below the boiling point of propylene, which is minus 48 degrees centigrade or minus 55 degrees Fahrenheit, okay, we would characterize that component as a light end. Therefore, if any component boils at temperature lesser than boiling point of propylene, we would call it as light end, and then we have to go for a gas recycle and purge stream. Now, newer technologies are available for separation of gaseous components like membrane processes, okay, but not much cost data is available where we can means while designing a membrane process. So, that factor we keep aside. When we go for no recovery or recycle of a particular reactant, obviously, when the reactant is cheap like water or air, now excess of these components are used in the process. For example, in combustion reaction, we use excess of air. However, air contains only 20% oxygen, 20 mole percent oxygen and 80% nitrogen, which is a relatively inert component. Therefore, when we choose excess, we have to define as how much excess, okay, because giving unnecessarily large quantities of air could put burden on your blower, okay, which uses electricity for operation. Okay. So, that point we also note. Excess of components used, specify excess, use of unnecessarily large quantities, could cause burden on equipment and increase the operating cost. Then we see the decision of the number of product streams. The products and byproducts emerging from the process, what is their destination, and what is their fate. what we would ultimately do with these products and byproducts. Now, a thumb rule that governs the number of product stream is that never separate and remix two streams. Now, to decide upon the number of product streams, we will have to list all the components that leave the process or leave the reactant. Leave the reactor. Okay. Now, what are the component classification? Numerous components will leave the reactor, but how do you classify them? Component classification. We need to classify these components before we decide the destination of them. First category of components is the gaseous byproduct. And the feed impurities, that would come out of the reactor unreacted. Then second is gaseous reactants, unreacted. Now, these unreacted reactant may also contain some inerts. Then third category is reaction intermediate. Then azeotropes with reactants. Then the reversible byproduct. We put them in the same category. Then the liquid reactant the primary product. Then valuable byproduct. Then the byproducts that could be used as fuel and byproducts that need treatment before disposal. Now, some reactants may not be recovered and recycled. So, we list them separately. Gaseous or liquid reactants not recovered and recycled. Okay. Now, let us see what is the destination of each of these category of components. The gaseous product the gaseous byproducts and feed impurity, if they are small in quantity, they could be vented. However, we need to scrub this gas to remove the polluting components. Okay. Then the gaseous unreacted reactant plus inert. Now, you have here the option of recycle and purge. Reaction intermediate, azeotropic reactants, reversible byproduct, you have the option of recycling them. You may also remove them, but it is better to recycle them back to the reactor. Primary product and valuable byproduct will go to packing and further processing, or let us say packing and further processing. Byproducts that are used as fuel may go to furnace or other heat exchange equipment that is in the process. The waste byproducts or liquid byproducts that need waste treatment to remove or to lower the BOD and COD may go to effluent treatment plant. And the gaseous and liquid reactants that are neither recovered nor recycled can leave the process, or it could be, let us say, they exit the process. Gaseous reactants can be simply vented, liquid reactants can be drained. Now, while evaluating a flow sheet, we have to ensure that all reactants, unreacted reactants and byproducts and products leave the process. At each stage, we have to evaluate the flow sheet, and the thumb rule that we use is that make certain that all products, byproducts and inerts leave the process. This is a thumb rule that we use for evaluation of the flow sheet. Now, let us take example of the HDA process. The input output structure of the HDA process would look like this. You have two feed streams, the gaseous feed stream of hydrogen with inert methane as impurity, and then toluene, and the main product is benzene. Side product, if it is recovered and not recycled, is diphenyl, and then you have the recycle and purge stream containing methane and hydrogen. Now, the impurity, main impurity in hydrogen is methane, okay, and we have to make sure that while designing a process, all inert that enters with fresh feed hydrogen should leave with the purge. Okay. We also need to consider what are the impurities that could be present in toluene. Now, these impurities can give further side reaction like formation of terphenyl or etc. However, to make the process operable, we have to make sure that all products, byproducts and inert leave the process. That is a thumb rule. If any inert is not removed, then it may build up in the recycle loop and then will make process inoperable. So, in this lecture we have seen certain decisions for deciding the input output structure of the flow sheet. In the next lecture, we shall try to identify the major design variables, and then we shall try to do an overall material balance around the process, and then evaluate the cost of various streams, feed streams, product streams, byproduct stream, purge stream, and then finally decide the economic potential of the process.